For almost a century, Pluto was treated as the forgotten world at the edge of our solar system. It was discovered in 1930, celebrated as the ninth planet, placed in textbooks around the world, and then, in 2006, reclassified as a dwarf planet. For decades, Pluto looked like little more than a frozen rock drifting billions of kilometers from the Sun. Then New Horizons arrived. After traveling for more than 9 years, the spacecraft flew past Pluto in 2015 and transformed our understanding of the distant world almost instantly. There were mountains made of water ice. There were vast plains of frozen nitrogen. There was a thin blue atmospheric haze. And there was the enormous heart-shaped region that became one of the most recognizable landscapes in the solar system. Pluto wasn't dead. It was active. But New Horizons only gave us a brief glimpse. The spacecraft raced past Pluto at incredible speed, observing the dwarf planet for a short period before continuing deeper into the Kuiper Belt. So scientists were left with a question. What was happening on Pluto when nobody was looking? That's where modern observations with the James Webb Space Telescope become important. Webb cannot fly past Pluto. Instead, it studies the faint infrared light coming from the distant world, allowing scientists to investigate its atmosphere, surface chemistry, temperature, and the behavior of molecules that are difficult to detect from Earth. And what we have learned about Pluto is far stranger than the frozen ball scientists once imagined. Start with the atmosphere. Pluto's atmosphere is incredibly thin compared with Earth's. It is dominated by nitrogen, with methane and carbon monoxide also present. At first, that might not sound particularly impressive. But Pluto's atmosphere behaves in a way that makes the dwarf planet remarkably dynamic. The atmosphere changes with Pluto's enormous 248-year journey around the Sun. When Pluto moves closer to the Sun, frozen nitrogen and other substances on its surface can sublimate directly into gas. When Pluto moves farther away, those gases can freeze back onto the surface. The planet essentially breathes. Its atmosphere expands and contracts as it travels around the Sun. And above that atmosphere is something even stranger. A giant layer of haze. Sunlight at Pluto is incredibly weak compared with sunlight here on Earth. Yet even that faint radiation is powerful enough to trigger complicated chemistry in Pluto's atmosphere. Ultraviolet light breaks methane molecules apart. The resulting fragments react with other molecules. More complicated hydrocarbons form. Eventually, some of these compounds become larger particles known as tholins. Those particles can drift downward and settle onto Pluto's surface. Over enormous periods of time, they contribute to the reddish and brownish colors visible across parts of the dwarf planet. So Pluto is effectively manufacturing complex organic chemistry in an atmosphere where temperatures are hundreds of degrees below freezing. And this is where the story becomes particularly interesting. Tholins are not life. They are not evidence that Pluto contains living organisms. But they are organic compounds, and organic chemistry is important because it provides some of the raw molecular ingredients involved in planetary chemistry and, under the right conditions, the chemistry associated with life. On Earth, early organic chemistry may have played a role in the chain of reactions that eventually produced biology. On Pluto, those same broad chemical ingredients are being created in an environment so cold that they can remain frozen for enormous periods of time. It's almost like a chemical laboratory operating in deep darkness. But Pluto's chemistry doesn't stop there. Its atmosphere can actually escape. Pluto is small. Its gravity is weak. Molecules in its upper atmosphere can gradually escape into space. And some of that material can travel toward Pluto's largest moon, Charon. Charon is enormous compared with Pluto. The two worlds are so closely connected gravitationally that they are sometimes described as a binary system. Charon is tidally locked to Pluto, meaning the same side of the Moon always faces the dwarf planet. And Charon has a mysterious reddish region around its north pole. Scientists have long suspected that material escaping from Pluto could contribute to this coloration. Methane escaping from Pluto can travel through the space between the two worlds. When it reaches Charon, some of it can freeze onto the Moon's surface. Then sunlight and radiation alter the chemistry. Over time, the material can become darker, more complex organic residue. In other words, Pluto and Charon are not completely isolated worlds. They are chemically connected. One world loses material. The other can collect it. Radiation then transforms that material over time. A process that unfolds so slowly that a human lifetime represents almost nothing compared with the age of the system. And Pluto's surface is just as strange. One of the most spectacular discoveries from New Horizons was the enormous Sputnik Planitia, the bright region forming the left side of Pluto's famous heart. The landscape contains frozen nitrogen and shows evidence of movement. Even at temperatures that would instantly freeze almost anything familiar on Earth, Pluto's volatile ices can flow and reshape the surface. Then there are Pluto's mountains. Some rise several kilometers above the surrounding terrain. They are primarily made of water ice. That sounds surprising until you remember how cold Pluto is. At Pluto's temperatures, water ice behaves more like rock. The mountains are effectively enormous ranges of frozen stone. But some of Pluto's most unusual terrain may have a different origin. Scientists have identified structures that resemble cryovolcanic formations. Instead of molten rock erupting from deep underground, cryovolcanoes would involve much colder materials such as water, ammonia, or other volatile mixtures moving through the crust. If Pluto really experienced cryovolcanic activity, something must have provided enough internal energy to keep material beneath the surface mobile. And that leads to one of the biggest mysteries of all. Could Pluto have, or once have had, a subsurface ocean? It sounds impossible. Pluto is incredibly far from the Sun. The sunlight there is weak. The surface is brutally cold. Yet planetary scientists have developed models in which Pluto could retain liquid water beneath its frozen exterior. Radioactive elements inside the rocky core can release heat. That heat does not disappear instantly. Over geological timescales, internal energy can remain important. A thick insulating layer of ice could also help preserve heat beneath the surface. That means the possibility exists that beneath Pluto's frozen crust there could be a hidden reservoir of liquid water. Not an open ocean beneath sunlight. A dark ocean trapped beneath kilometers of ice. And if that ocean exists today, it would completely change how we think about Pluto. Because the outer solar system would no longer simply be a collection of frozen, inactive objects. It would contain worlds with internal heat, chemistry, geological activity, and possibly liquid environments hidden beneath their surfaces. But there is another feature of Pluto that looks almost alien. Tartarus dorsa. This region contains enormous blade-like ridges made largely from methane ice. They form parallel structures across the landscape. From a distance, they look almost like a gigantic frozen forest or a field of ice knives. Similar processes can produce penitente-like structures on Earth, where sunlight and sublimation gradually sculpt snow and ice into sharp formations. But on Pluto, everything happens under radically different conditions. The Sun is only a tiny bright object in the sky. The atmosphere is extremely thin. The ground is dominated by frozen nitrogen, methane, and water ice. And yet the surface is still being shaped.